Start at 0 and walk along the whole numbers. At each step you take a jump, and the jumps get one longer every time. First a jump of 1, then 2, then 3, then 4, on and on. The only choice you ever make is direction. You would rather jump backward, toward the small numbers, but you are only allowed to if you land on a positive number you have never visited before. If you cannot, you jump forward instead. Watch the first few. From 0 you cannot go back, so you step forward to 1. From 1, a jump of 2 backward would land on -1, off the line, so you go forward to 3. From 3, a jump of 3 lands exactly on 0, which is not positive here, so forward again to 6. And now, for the first time, something gives. From 6, a jump of 4 backward lands on 2. 2 is positive, and you have never been there, so you take it. That single rule is the whole machine. There are no random choices, no hidden inputs. Given where you are and which step you are on, the next number is completely determined, and yet the path it traces refuses to calm down. Let us pin the rule down exactly, because everything later hangs on it. You are standing on the last number you reached. The step count is some value, call it n. You look backward first, subtract n. If the result is positive, and it is a number not already in your trail, you move there. Otherwise, and only otherwise, you add n and move forward. So there are exactly 2 ways the backward move can be blocked. Either it would carry you to 0 or below, off into the negatives, or it would drop you onto a number you have already used. Either failure sends you forward by the same amount instead. That is the entire law. Notice it is greedy in one specific way. It always tries to come back down toward the small numbers, and it only climbs when it is forced to. This tension is the source of everything. A pull downward, resisted by the rule that you can never reuse a spot and never touch 0 or the negatives. The sequence spends its whole life trying to squeeze into the gaps it left behind. Numbers in a row hide what this thing is really doing, so draw each jump as a half circle. Every time you move from one number to the next, connect them with a semicircle whose diameter is exactly that jump. Because the jumps grow, the arcs grow with them. To keep them from piling on top of each other, alternate. The first arc curves above the line, the next below, the next above, and so on. What appears is unmistakable once you have seen it. A run of nested and interleaving half circles, some tiny, some sweeping clear across the picture, looping over and under the same stretch of number line again and again. This is the signature of the sequence, the thing people recognize it by. Nothing here was chosen for looks. Every arc is forced by the rule. The radius of the arc at step n is exactly n over 2, and whether it goes over or under is just whether n is odd or even. The wild picture is a faithful portrait of a completely rigid law, and the arcs carry information you can read directly. Since the diameter of each half circle is the step number, the arcs get uniformly wider as you go, 1 unit of diameter per step. A backward jump and a forward jump on the same step draw the very same size of arc, only the direction differs. So the picture is really a running record of the tug between going back and being pushed forward, written in nothing but half circles. Look at what the arcs are telling you. The big sweeping ones carry you far to the right. The small tight ones are the sequence darting back to the left to grab a low number it skipped. It is a tug of war between climbing and returning, and the two sides are almost evenly matched. Over the first 1,000 steps, the sequence jumps backward 493 times and forward 506 times. Nearly a coin's balance, yet not from chance. Each backward jump is the rule cashing in on a gap that opened up. Each forward jump is the rule being denied and forced to climb. Because it climbs only when blocked, the sequence never runs away and never settles. Across those same 1,000 steps, it wanders as high as 3,685, then comes plunging back toward the small numbers whenever a backward door opens. On average, it drifts upward, roughly in step with how big the jumps have gotten, but it is forever diving back down to scoop up something it left behind. That restlessness is exactly why filling in every integer is so delicate. Here is the first genuine surprise, and it breaks something you might have assumed. You might guess that since the rule forbids repeating a number, every value shows up at most once. That is wrong. The rule only blocks a backward jump onto an old number. It says nothing about a forward jump. So the sequence can be forced forward, by addition, straight onto a value it already visited long ago. It happens for the first time at the 25th term. The number 42 appears at step 20, and then again at step 24, landed on from the other side by a forced forward jump. This matters more than it looks. It means the sequence is not a clean shuffle of the whole numbers, where each one appears exactly once. Some appear twice. So there are really two different questions hiding here. Does every integer appear at least once? And does every integer appear exactly once? The second one already has an answer, and the answer is no. That leaves the first question. Does every whole number appear at all, eventually? Watch the sequence fill in the low numbers, and you would swear the answer is an easy yes. 0, 1, 2, 3, all present in the first handful of steps. But some of the small numbers are shockingly stubborn. Take 5. It looks trivial, yet the sequence does not actually land on 5 until the 129th step. And then there is 19. 19 is a tiny number. You would expect it early. It does not appear until step 99,734. So to simply cover every integer from 0 up through 20, you have to generate almost 100,000 terms, and it is 19 that makes you wait. If a number that small can hide that long, you cannot trust your eyes about the big ones at all. The pattern of who arrives when has no visible rhythm. It just happens to work out so far. Push the goalpost a little further and the weight explodes. To cover every integer from 0 up through 100, you need over 180,000 terms. Each new small number you demand can cost you tens of thousands of extra steps, because the sequence only returns to a gap when the arithmetic happens to line up a legal backward jump onto it. Nothing schedules these visits. They arrive when they arrive. So we arrive at the real question, the one nobody can answer. Does every single non-negative integer eventually appear somewhere in this sequence? Everyone who has looked believes the answer is yes. Computers have run the sequence out to many billions of terms, and every integer they can reach does turn up sooner or later, 19 included. But believing is not proving. There is no argument that guarantees some particular number is not skipped forever. In fact, as of the large searches that have been done, there is a smallest number that has never been shown to appear at all. It is 852,655. Every number below it has been found. That one, so far, has not. That is the open problem in one sentence. A rule simple enough to teach in 10 seconds. And we cannot say whether it reaches every number or leaves one behind forever. And the gap between what we have checked and what we can prove is enormous. The searchers that turned up that missing number combed through more terms than there are seconds in 100,000 years, and still every integer below 852,655 was accounted for. That is overwhelming evidence and exactly zero proof. A single stubborn number, hiding the way 19 hid but never coming out, would be enough to break the conjecture, and no one has found a reason it cannot happen. There is one more way people have come to know this sequence, and it is not visual at all. Map each term to a musical note, low numbers to low pitches, high numbers to high, and play them in order. Because the sequence lunges forward and snaps back, the melody does the same. It skitters, it leaps, it darts back down, restless in exactly the way the arcs are restless. Neil Sloan, who catalogs sequences for a living, has pointed to this one as a favorite to listen to, precisely because that jagged motion is audible. The point is that a single deterministic rule, with no randomness in it anywhere, generates something your ear hears as almost improvised. The complexity was never added. It was already folded inside subtract, or if you cannot, add. So here is the whole thing, start to finish. Begin at 0. At step n, jump back by n if you land somewhere positive and new. Otherwise, jump forward by n. Draw each jump as a semicircle, and you get that unmistakable tangle of nested arcs. From that one line come all the surprises. It revisits numbers, so it is not a perfect shuffle. It hides small values for tens of thousands of steps, before finally catching them, and whether it truly sweeps across every integer, touching all of them, is a question that has resisted everyone who has tried. If you remember one thing, let it be this: the shortest rules can hide the longest questions. This one you can write on a napkin, and it still has the last word.